In this video, we'll study about the Cauchy's residue theorem and the problems relating to Cauchy's residue theorem. If f of z is analytic within and on a closed curve C, except at a finite number of singular points a1, a2 and so on an within a curve C, and r1, r2 and so on rn be the residues of f of z at these singular points or poles, then integral over C f of z dz is equals to 2 pi I into r1 plus r2 plus r3 and so on rn. That is, integral over C f of z dz is equals to 2 pi I into sum of the residues. So draw a circle C1 around the singular point A1. Similarly, draw a circle C2 around A2. So, like that, continue for all drawing circles around all the singular points. These circles are such a way that they are non-overlapping circles, and each circle will include only one singular point. Then C1, C2 and so on Cn along with C will form a multi-connected set. Multi-connected set. So we can apply Cauchy's theorem on this multi-connected set. So according to the Cauchy's theorem, integral over C f of z dz is equals to integral over C1 f of z dz plus integral over C2 f of z dz and so on integral over Cn f of z dz. This is given by 2 pi I to residue of f of z at z is equals to a1 plus 2 pi I into residue of f of z at z is equals to a2 and plus so on 2 pi I into residue of f of z at z is equals to an. So this we can write it as 2 pi I residue of f of z at z is equal to a1 is given by r1 plus 2 pi I into r2 and plus so on 2 pi I into Rn. This is equals to 2 pi I R1 plus R2 and so on plus Rn. This is the proof of the Cauchy's residue theorem. Now we'll move to the problems on Cauchy's residue theorem. So evaluate the integration over C 1 plus Z by Z into 2 minus Z dz, where C is the circle, mod Z equal to 1 using residue theorem. So let f of Z is equals to one plus Z by Z into 2 minus Z. So f of Z as poles or singular points, as poles at Z is equal to 0 and Z is equals to 2. So the given curve is a circle, mod Z is equals to 1. So modulus of Z is given by under root of x square plus y square equals to 1. Squaring both sides, we get x square plus y square equals to 1, which represents a circle whose center is at origin and radius 1 unit. So I'll go for a circle, center at origin and the radius is 1 unit. If I look at these poles, Z is equal to 0 and Z is equal to 1, they are simple poles. So these poles, we have to check whether they lie within the circle or not. So Z is equal to 0, S that lies inside, and when go for Z is equals to 2, it lies outside because the radius is 1 unit. So Z is equal to 0 lies within the C, and Z is equal to 2 lies inside the curve C, and Z is equals to 2 lies outside the C. So I'll go for the R1. R1 is nothing but a residue of f of Z at Z is equals to 0. So this equals to limit Z tends to 0, Z into f of Z. So this is limit Z tends to 0, Z into 1 plus Z by Z into 2 minus Z. So substituting the limit, so 1 plus z by 2 minus z. So there is 1 by 2. So now integral over c f of z dz equals to 2 pi I into r1. Since we have only one residue, so 2 pi I into 1 by 2 is equals to pi I. Next we'll move to the problem 2. Here f of z is z square by z plus 2 into z minus 1 whole square, where c is the circle given by mod z equal to 3. So let f of z equals to z square by z plus 2 into z minus 1 whole square. F of z has poles or singular points, poles at minus 2, which is a simple pole, and f of z as pole at z is equals to 1, which is a pole of order 2, which is a order 2 pole. Now the given curve is mod z equal to 3. So this implies x square plus y square is equals to 9. So this is a circle, center at origin and radius 3 units. So minus 2 is 0 and plus 1 is 0. So both the poles z is equals to minus 2 and z is equals to 1 lies inside the circles z is equal to 3. So we need to evaluate the residue of f of z at z is equals to minus 2 and at z is equals to 1. residue of f of z at z is equals to minus 2. Let this be R1. So this is, since it is a simple pole, limit z tends to minus 2, z plus 2 into z square by z plus 2 into z minus 1 whole square. Can cancel out z plus 2, and by substituting the value z is equals to minus 2, we get minus 2 whole square by minus 2 minus 1 whole square. So this is 4 by minus 3 whole square is 9. Now we'll move to the second residue, R2. R2 is residue of f of z at z is equals to 1. So since it is order to pole, so this will be given by 1 by 2 minus 1 factorial limit z tends to 1 d by dz of z minus 1 whole square z square by z plus 2 into z minus 1 whole square. So we can cancel out z minus 1 whole square and z minus 1 whole square. Here we have to apply derivative of u by v. So derivative of u by v, that is d by dz of u by v, is given by v square v into derivative of u minus u into derivative of v. So this gives, so this is the formula. So this is 1 by 2 minus 1 factorial is 1. So limit z tends to 1. Now we'll be applying u by v. So denominator is z plus 2. So I'll get here z plus 2 whole square z plus 2 into derivative of the numerator 2z minus u into, so z square into derivative of denominator is 1. Now by substituting the value, so 3 into 2 minus 1 by 1 plus 2 whole square. So 6 minus 1 5, 5 by 9. Now integral over f of z dz given by 2 pi I into sum of the residues R1 plus R2. So this is 2 pi I 4 by 9 plus 5 by 9. So this is equals to 2 pi I. Now we'll move to the problem number 3. Let f of z is equals to 1 by z square plus 4 whole square. To get the poles of f of z, equate denominator to 0. So z square plus 4 whole square equal to 0. This implies z square plus 4 equal to 0, or z square is equals to minus 4, implies z is equals to plus or minus 2i. So f of z has poles at z is equals to 2i, that is equals to minus 2i. Each of order 2. Since we have whole square, so each pole is of order 2. And the given curve is mod of z minus I equals to 2. That means mod of x plus iy minus I is equals to 2. So implies x plus y minus 1 into I is equals to 2. Or I can write as x square plus y minus 1 whole square is equals to 4. Taking the modulus and squaring both sides, we get this. So which is the circle at center at 0, 1. Circle center at 0, 1 and radius 2 units. Now to check whether these poles lies inside or outside the circle, we substitute z is equals to 2i in mod of z minus I equal to 2. So this is mod of 2I minus I is equals to mod of I, which is equals to 1, and this is less than 2. So this implies Z is equals to 2, I lies inside. So it is less than 2 lies inside the circle, and if it is greater than 2 lies outside the circle. Now we'll check Z is equals to minus 2I lies inside or outside. So put Z is equals to minus 2I in mod of Z minus I equals to 2. Mod of Z is minus 2I minus I, which is modulus of minus 3I, is equals to 3, greater than 2. So Z is equals to minus 2I lies outside T. Now we'll go for residue at Z is equals to 2I. Residue of f of Z at Z is equals to 2I. So which is equals to 1 by 2 minus 1 factorial limit Z tends to 2I d by dz of Z minus 2I whole square into f of Z. F of Z is Z square plus 4 whole square. Now this is limit 2 minus 1 factorial is 1 factorial, so 1. So I write your limit Z tends to 2I d by dz of Z minus 2I whole square. This function we can write it as Z minus 2I whole square Z plus 2I whole square. So we can cancel out Z minus 2I whole square. Now limit Z tends to 2I the derivative of 1 by z plus 2y whole square is minus 2 by z plus 2y whole cube. Now substituting the limit, we get minus 2 by 4i whole cube. 2i plus 2i is 4i whole cube. So which is minus 2 by 4 cube is 4 and I cube. Since I square is 1, we can write this as 2 by 64i. Since z is equals to minus 2i lies outside, so we not consider the residue of f of z at z is equals to minus 2i. So by residue theorem, integral over c 1 by z square plus 4 whole square dz equals to 2 pi I into sum of the residues. Here we have only one residue. So 2 pi I into residue of f of z at z is equals to 2i. So this equals to 2 pi I into 2 by 64i. So this equals to pi by 16, which is the required integral value. Now we'll move to the problem number 4. Here we take f of z as z minus 3 by z square plus 2z plus 5. So to get the poles, so equate denominator to 0. So here we don't get the roots, so we use the formula z is equals to minus 3 plus or minus b square minus 4ac by 2a. So which is equals to minus 2 plus or minus under root 4 minus 20 by 2. So which is equals to minus 2 plus or minus under root minus 16. So we can write this as 16i square by 2. So this equals to minus 2 plus or minus 4i by 2. So moles are minus 1 plus or minus 2i, and these are simple poles. Now the given curve is mod of z plus 1 minus I equals to 2. So which is a circle center at minus 1 comma 1 and radius 2 units. To check whether this pole lies inside the circle or not, we substitute z is equals to minus 1 plus 2i in the circle. Put z is equals to minus 1 plus 2i in mod of z plus 1 minus I equals to 2. So we get mod of minus 1 plus 2i plus 1 minus I is equals to modulus of I. Since plus 1 and minus 1 will get cancelled, 2i minus I is I, which is equals to 1 less than 2. So this implies z is equals to minus 1 plus 2i lies inside circle. Now we'll check the second pole, minus 1 minus 2i lies inside the circle or not. So put z is equals to minus 1 minus 2i in mod of z plus 1 minus I equals to 2. So we get here minus 1 minus 2i plus 1 minus I is equals to modulus of minus 3i, which is equals to 3 and greater than 2. So this implies z is equals to minus 1 minus 2i lies outside C. Now we'll go to the residue of f of z at z is equals to minus 1 plus 2i. This lies inside the circle. This is simple pole. So limit z tends to minus 1 plus 2i z plus 1 minus 2i into f of z. So this is limit z tends to 1 plus 2i z plus 1 minus 2i. F of z is z minus 3 by, write this in terms of factors so that we can cancel out. Z plus 1 minus I z plus 1 plus 2i. These two terms will get cancelled, and by substituting the limit we get minus 1 plus 2i minus 3 by minus 1 plus 2i plus 1 plus 2i is minus 4 plus 2i by one, and minus 1 will get cancelled, we get 4i, so which is equals to minus 2 plus I by 2i. Now from residue theorem, integral z minus 3 by z square plus 2z plus 5 dz equals to 2 pi I to residue of f of z at z is equals to minus 1 plus 2i, which is equals to 2 pi I minus 2 plus I by 2i. So by cancelling it out we get 5 into minus 2 plus the required integral. Thanks for watching this video, and look for some more videos to this channel. Please don't forget to subscribe the channel. Thank you.